Okay, there is a table in chapter 27, and it tells you some characteristic numbers of the conductivity, actually resistivity. And you can see from that table that there is a huge disparity, huge difference in the value of resistivity among different materials. In certain typical metals, such as silver and copper and gold, you'll find the resistivity in ohm meter is typically a very small value, indicating that these are excellent conductors. At room temperature, the best metallic conductor is silver, not gold. Okay, strangely enough, it's not gold, it's silver. And its resistivity is only about 1.6 times 10 to the negative 8 ohm meter. On the other hand, if you look at examples of insulators, okay, these are poor conductors of electricity, and they do not allow current to flow through easily, so we can use them as electrical insulators. An example would be quartz. Quartz has a humongous value of resistivity, 7.5 times 10 to the 16 ohm meter. And you can see the difference is, we're looking at 24 orders of magnitude. This is huge. You might ask, what accounts for this huge difference? What makes silver such an excellent conductor and quartz such an excellent insulator? Well, the theory of electrical conductivity is not something we can fully understand, fully describe in classical physics. It actually belongs to the realm of modern physics. We have to use quantum mechanics to understand that, and only in physics 1D are we going to start to scratch the surface of this fascinating topic. But in a nutshell, when it comes to metallic conductors such as silver and gold and copper and so forth, as you know, what makes them excellent conductors is the availability of free electrons. These are electrons that no longer belong to individual atoms. Okay, they can freely, more or less freely travel, move within the entire interior of the conductor. And electrons are very light, they're very mobile, so once you have a small electric field, these electrons will start to flow, causing a current. And that is what's responsible for the high conductivity or low resistivity of all metals. And again, the best example would be silver. On the other hand, in insulators, there are no such available charge carriers that are free to move. In quartz, for example, all the electrons are tied to individual atoms. They cannot break away from their parent atoms under normal circumstances and travel freely within the quartz interior itself. So therefore, quartz is a good insulator because of the lack of conducting charges. Okay, but the details is far from that, and like I say, we're going to start to study the basics of that in Physics 1D. Now, besides these two extremes, conductors and insulators, we also have some novel materials with interesting properties when it comes to conduction. One is so-called superconductors, and the other is called semiconductors. Okay, what is a superconductor? Well, the very term suggests that this is a material which conducts electricity better than anything. Okay, they're called superconductors. As a matter of fact, superconductors can conduct electricity with virtually no resistance. It's better than the best metal under normal circumstances. Superconductivity was discovered in the year 1911 by the Dutch physicist Kamerlingh Onnes. Okay, this happens only when the temperature drops below a certain critical value called Tc, C standing for critical. And that value, Tc, varies from material to material. In the case of mercury, mercury is a normal conductor. It's a good conductor at normal temperature. But when you cool down mercury, you find, strangely enough, at a certain temperature, in this case 4.2 Kelvin, very, very close to absolute zero, okay, very, very cold, all of a sudden, the resistivity of mercury drops to virtually zero, okay, and it stays that way all the way to absolute zero. So we say mercury has entered from the normal state to a superconducting state, which is characterized by the total absence of resistivity. Okay, the phenomenon of superconductivity is fascinating, but we can only start to understand what's going on when we study modern physics in Physics 1D. But it suffices to say that superconductivity is a very important phenomenon that's being studied by theoretical physicists, and also its applications are being researched upon by many other scientists. It is possible with the availability of superconductivity, for example, that we can make superconducting rails that can on which trains can move at extremely high speeds, that sort of thing. So in principle, this is something that can find many important applications, which we'll study later. What about semiconductors? Well, as you undoubtedly have heard, semiconductors are at the very heart of modern computers. In fact, all modern electronics, not just modern computers, are based on semiconductors. Okay, we're talking about silicon, germanium, that sort of thing. Okay, semiconductor. What's so good about semiconductors, you may wonder? Well, if you want to conduct electricity well, you use metals, right? These are conductors. And if you want to insulate them, you use insulators. So what's good about semiconductors? This is somewhere in between, right? By definition, the conductivity of semiconductors somewhere in between metals and insulators. So why do we find them useful? Well, the interesting thing about semiconductor is not because their conductivity is somewhere in between. Okay, there are many reasons why semiconductors are useful, but one of the biggest reasons is that the properties, okay, the electrical properties of semiconductors are tunable. They can be adjusted. Okay, in fact, a pure piece of silicon, it's called what's called an intrinsic semiconductor. It's got some use, but it's not the biggest reason why we're interested in semiconductors. But when you take this piece of silicon and you put some other materials into it, okay? In other words, in physics we say we dope it, okay? We dope it with other atoms such as aluminum, such as germanium, okay? And then as a result, what you find is that the conductivity can change dramatically. Okay? The conductivity can change dramatically. And also, the conductivity or resistivity also changes dramatically as a function of temperature as well. And it's a dramatic decrease in resistivity as the temperature rises. It's some sort of exponential function instead of a more more common linear function as you would find in metals. So it is this versatility of semiconductors which can behave as a good insulator and a good conductor and anywhere in between under the right conditions that makes semiconductors so versatile and so useful. And again, we are only going to study some details in 1D, not here. Now, speaking of temperature dependency, for a typical metal, this is what we expect as temperature changes as far as the resistivity is concerned. The resistivity plotted as a function of temperature. In the absence of superconductivity, not all metals are superconductors at low enough temperature. So this is a piece of metal without any superconductivity behavior at low temperature, and here's what happens. It turns out that at high enough temperature, you find that the resistivity, roughly speaking, is a straight line. Okay, it increases linearly as a function of temperature. As temperature becomes really low, it sort of flattens out and reaches a certain saturated value. Okay, now we cannot understand this in qualitative terms without enough knowledge of the microscopic behavior of the conducting electrons in a piece of metal. But at least we can qualitatively understand why the resistivity would rise in a piece of metal as the temperature rises. Okay, you understand that the reason why there is a resistance at all is because the electrons, the conducting electrons, cannot simply travel from one place to another without any interference, without any interruption. Rather, they collide frequently, right? They collide frequently. And any collision would interrupt the acceleration process by the external electric field, because and you imagine if that doesn't happen, okay, there is no collision. The electron keep on getting accelerated by this external electric field, uninterrupted. Then as the electron keeps on going, it picks up more and more speed. It's going to accelerate, and that's going to increase the current density, right? So the current density will then rise as a function of time. Now we know that doesn't happen. Rather, the current density reaches a certain value based on the conductivity and the external electric field, and that is because in a real metal, any conducting electron will collide frequently. Okay, so their path is frequently interrupted, and that is the origin of resistance. Now imagine that when the temperature rises, what happens? When the temperature rises, first of all, the electrons will move faster on average, right? Their random motion speed is faster. Okay? And so it takes less time for them to move from one collision to the next collision because they move faster. And secondly, the electron will collide with lattice ions. These are the positive atoms, positive ions that form the backbone of the metal. And these lattice ions now would oscillate with greater amplitude. Okay, so they also start to move around, and that makes it easier for them to collide with the electrons. So, at any rate, as the temperature rises, the collision becomes more frequent. That's more interruption for the acceleration process caused by the external electric field, and therefore the resistance would rise. Okay, so at least you can understand qualitatively why it would go up. Why it would go up, and it's roughly a linear function. And we need to describe this linear function. Suppose at a certain temperature T0, the resistivity is rho naught. Okay, so that's that point. And beyond that point, we expect a linear function. So it is clear that I can write rho as rho naught times this linear function. 1 plus alpha T minus T0. So you see, as T equals T0, this term goes to 0, so rho equals rho naught, right? And alpha is called a temperature coefficient of resistivity. It has to do with the slope of this line. It's not equal to the slope. Actually, the slope equals rho naught times alpha. Okay, the intercept is rho naught. Now, alpha typically is a quite small value for metals. Otherwise, you would expect a dramatic change in the value of rho as temperature changes, and we know that is not the case. If you go back to table 1, chapter 27, you'll find that the temperature coefficient alpha for most metals, they're of the order of 10 to the negative 3, okay, in SI system, and the unit would be 1 over degree Celsius because it cancels with the unit of T. So that's quite small. So you can expect a small change, okay, a small change in resistivity as the temperature changes, but not a dramatic one, unless the temperature changes quite a lot.